19 days before this bridge collapsed, cracks appeared in the concrete. They did not stay small, they lengthened, they widened. Photographs circulated between the engineers and contractors. On the morning of March 15, 2018, the project team met beside the bridge specifically to discuss them. Their conclusion was that the cracks presented no safety concern. Hours later, workers began retentioning steel rods inside the structure. Traffic continued underneath. At 1:46 p.m., the bridge fell onto Southwest 8th Street in Miami. 6 people died and 10 were injured. The concrete was strong enough. The steel met specification. The hydraulic equipment worked. The failure was already built into one connection, and the cracks were the structure drawing its own warning diagram. The Florida International University Pedestrian Bridge was meant to create a safer crossing over 8 lanes of traffic. Its 174-foot main span was assembled beside the road and moved into place in a highly publicized operation. Visually, it resembled a cable-stayed bridge. But during this stage of construction, the tower, backspan, and stay cables were not yet carrying the main span. The span supported itself between 2 piers. Its structural core was a concrete truss, a deck below, a canopy above, and a single line of diagonal concrete members joining them down the center. That single line mattered. The National Transportation Safety Board later concluded that the bridge had only one load path. If a critical connection failed, there was no alternate system waiting to carry the weight. At the north end, diagonal members numbered 11 and 12 met the deck at a region engineers called Node 1112. The bridge's enormous self-weight pushed force through that node and toward the end support. The connection's job was to resist that sliding action, interface shear, across concrete poured at different times. Imagine placing a heavy book on a board, then tilting the board. Friction and fasteners keep the book from sliding. At Node 1112, rough concrete surfaces, reinforcing bars crossing the joint, and compression were supposed to transfer the force safely. But this was a cold joint. The deck concrete had hardened before the diagonal member was cast against it. The 2 pours did not behave like one seamless piece of stone. Their interface had to be deliberately designed to carry shear. The investigation found 2 fundamental calculation errors. First, the design team underestimated the demand, the force the node actually had to resist. The NTSB's comparison found that demand was nearly twice the value used by the designer. Second, the design overestimated the node's capacity to resist that force. Even the construction drawings did not consistently require the surface roughness assumed in the calculations. Investigators emphasized that proper roughening alone would not have saved the underdesigned node. This was not weak concrete. It was a connection being asked to carry more than its design said it would, with less resistance than the design credited to it. When the span began supporting its own weight, the calculation problem became physical evidence. Cracks appeared around Node 1112. Over the next 19 days, construction and inspection teams photographed and reported them. Some were measured several inches deep. The distress grew around the exact region that would initiate the collapse. The engineer of record repeatedly said the cracks were not a safety concern. A repair plan focused on retentioning rods inside member 11, effectively squeezing the diagonal member harder against the connection. On the morning of the collapse, representatives from the designer, contractor, inspection firm, university, and transportation department met to discuss the cracking. According to the NTSB, work continued without an independent review of the proposed repair and without closing the road below. This is the point where the story stops being only about a calculation. A calculation can be wrong. Engineering safety depends on the layers around it. Independent checking, inspection, escalation, and the willingness to remove people from danger when the structure begins contradicting the model. Here, each layer had information. None stopped the exposure. The project required an independent peer review. A separate engineering firm certified the design, but it did not evaluate the truss nodes or all of the temporary construction stages. The reviewer later acknowledged that those elements should have been examined, but said the budget and schedule were insufficient. The NTSB also found that the firm was not qualified for the category of complex concrete bridge work it had been hired to review. That omission was crucial, because the bridge that failed was not yet the completed bridge. Engineers do not design only the final object. They must design every temporary state used to create it. A structure may be stable after all its components are connected and still be vulnerable while half finished. At the moment of collapse, this span lacked the future stay cable system and had to carry itself through the underdesigned node. The review missed both the critical location and the critical stage. As workers retentioned member 11 on March 15, the node was already severely distressed. According to the federal reconstruction, the demand at node 1112 exceeded its resistance. Reinforcing bars crossing the shear planes were pushed beyond their limits. Member 12 temporarily acted like a buttress, taking more of the load. Its reinforcement and surrounding concrete then failed. Concrete blew out at the north side of the connection. Members 11 and 12 shifted northward. Once that geometry unraveled, the single-line truss lost stability. With no redundant load path, the entire 174-foot span left its supports and fell approximately 18.5 feet. Investigators tested the obvious alternatives. The concrete and reinforcing steel met or exceeded project requirements. The post-tensioning rods met their mechanical requirements. The hydraulic jack was functioning correctly. The NTSB identified the probable cause as the designer's load and capacity calculation errors at node 1112. It identified the inadequate peer review and the failure to recognize the significance of the cracking as contributing causes. It said the severity was increased by the collective failure to stop work and close the roadway. A load path is the root force takes through a structure and into the ground. But this collapse reveals a second kind of load path. The root information must take through an organization before somebody acts. The physical load had one fragile path through node 1112. The warning had many paths: photographs, emails, inspections, a morning meeting, and visible cracks, but no effective destination. After the investigation, the NTSB recommended stronger guidance for calculating concrete interface shear, explicit review of construction stages and nodes, tighter qualification and oversight of peer reviewers, and clearer authority to halt work and close roads when structural distress appears. The most important lesson is not that cracks always mean collapse. Many concrete cracks are harmless. The lesson is that unexplained, growing cracks in a critical, non-redundant connection are new evidence. They demand that the model be challenged, not that the evidence be fitted to the model. The bridge was telling the project team where its load path ended. For 19 days, nobody treated that message as a reason to move the public out from underneath it.